This lecture is part of a series of lectures for Rad229 MRI Signals and Sequences offered in the Department of Radiology at Stanford University. The 13th lecture on sampling and timing is divided into two parts. Lecture-13A covers sampling and point spread functions. The learning objectives are to describe the relationship between case-based sampling and the point spread function, or PSF, to explain resolution, field of view, and case-based apodization using a PSF, to understand half-Fourier imaging effects and reconstruction, and to describe case-based modulation effects on the PSF. The point spread function is the Fourier transform of the sampling pattern. In case-base, we usually think about the extent, the density, and perhaps windowing. The effect on the point spread function is the width of the main lobe, the distance to replicas of the main lobes, and the ripple or side lobes, and the amplitude of these side lobes. So here we have case-based sampling, we take a Fourier transform, and we have the point spread function. Ideally, the point spread function would be a single point, and it has as narrow a width as possible. Of course, if we have a greater extent of case-base, we'll have a narrower width for the point spread function. The spacing in case-base will determine the field of view, and this is the distance between replicas of the point spread function. So let's consider basic Cartesian sampling and the point spread function. In Cartesian sampling, we sample finite extent case-based lines. These are finite extent in both kx and in ky. There is filtering along the readout direction. And the features of the point spread function are to have a non-zero width main peak, to have some ringing, to have replication in y, or the phasing code direction, and no replication in the x direction. So here's a picture. Here we've actually undersampled case-base by threefold. This is so that we can see the replication in the field of the point spread function in the phasing code direction, and these replicas are spaced apart by exactly a field of view over 3, or the field of view of the undersampled acquisition. We also see in the bottom right, we can plot the central part of the point spread function zoomed in, and we can see that we can plot a line plot both horizontally and vertically, and we can see the main lobe and the side lobes. And the width of the main lobe is roughly a pixel at the full width half max. So here's a question to warm up. When we consider the point spread function and Cartesian sampling, why is there no point spread function duplication in the readout direction? We've shown that there is duplication in the phasing code direction on the previous slide. The choices are A, B, and C, the samples being adequately spaced, the A to D filter suppressing duplicates, or the sampling being continuous. So the answer here is B. The A to D filter actually suppresses duplicates by literally filtering them away. Notice that choice A and C are both incorrect. The samples are not adequately spaced because with any discrete sampling, we would have some replication. And answer C is incorrect because the sampling is not continuous. When we consider the point spread function, it's also important to remember that we are sampling discretely. Therefore, we actually use a discrete sinc function rather than the continuous Fourier transform of a continuous rectangular window. The discrete sinc function looks like this, and this is a function of the extent with which we sample. And here you can see the discrete sinc function compared to the analog or continuous sinc function for a width of 32 and a width of 8 at the bottom. And you see that as we reduce n here, that the discrete sinc function has more ringing than the continuous sinc function. This just shows you that when you go to a low number of samples, that there are additional challenges or additional ringing. Usually, as you can see here, for 32 samples or more, this is not really a problem. However, in some cases in 3D imaging, you might have a low number of slices, and this could be a challenge. Let's look now at windowing in K-space, and the purpose of this is to reduce the ringing in the point spread function. So here's a picture with K-space in the top left with a Fermi filter that we'll describe shortly. On the right, you see the point spread function without the filtering, and then in the bottom right, the point spread function with the Fermi filter applied. And the bottom left is simply the point spread function zoomed out. So what you can see here is a slight reduction of the side lobes in the bottom right compared to the top right, and there's actually a slight broadening of the PSF. So this is quite subtle in this case, because we've used a very subtle Fermi filter actually. So there is a slight broadening of the PSF, and the Fermi filter is one approach. Other approaches are a Hamming window or other similar filters. And this is the form of the Fermi filter here, where A is some distance from the origin in X or Y, and sometimes this is circular as well. Let's look at the point spread function when we have variable density. So here we've used 2x undersampling. The spacing between K space samples is linearly increasing with the absolute value of K. This leads to minor aliasing, and the point spread function actually broadens. So you can see the broadening of the PSF in the bottom left where we've zoomed in on the central lobe. And you can see in the bottom plot here that there is a signal, but it sort of has a ringing appearance to it. It's essentially a high-pass filter. And so essentially you have aliasing of the high spatial frequencies, which makes intuitive sense because the spacing at the outer K-space points is these samples are spaced more further apart. Interestingly, if we apply density compensation, here we would multiply by delta K here, so that we weight the outer K-space samples more heavily to compensate for the lower density. In this case, we have no broadening of the point spread function. However, we have higher ringing because we've amplified these outer K-space point signals, and this is where we might have some aliasing. So we could apodize this, which is essentially similar to reducing that density compensation. So it's interesting to see that the variable density is actually providing a form of apodization. So density compensation, as with apodization, has a trade-off between increasing the ringing and reducing the width of the point spread function. So let's look at a question regarding SNR. When we have this case here, what happens to the noise in this sampling and reconstruction scenario? Here we have the variable density trajectory, and we've applied this density compensation. So the answer here, we have higher density at the center, so we have some averaging, and we have density compensation at the outer parts, which amplifies the noise. So what we see here is that the sigma for the noise as a function of K is the square root of the weighting that's applied across different K-space locations here. Let's look now at half-Fourier sampling and the point spread function. In half-Fourier sampling, we will literally sample half of the K-space. However, there are different ways to choose which half of the samples we choose. So in general, the full K-space sampling trajectory is capital S sub f of K, and the point spread function, let's assume, is a delta function. The half K-space trajectory we will call capital S sub h of K, and in one dimension, this is what this might look like, where we've essentially sampled half of the points of K-space. We've only sampled the negative K here. As a subtlety here, we've weighted the central point and the left outer point by 1/2. And this actually is important when you think about this, doing this discretely. However, when you do this continuously, it doesn't really matter. So when we do a half-Fourier sampling pattern, we're essentially setting the points in capital S sub h to 0 for either k or negative k from the fully sampled pattern. When we do this, there's a point spread function, which is little s sub h of r. Notice that capital S sub h of k is real valued, and it has an even part that is exactly half of the fully sampled trajectory. This means that the real part of the point spread function is 0.5 times the delta function. If we take a magnetization k multiplied by the sampling pattern, we can Fourier transform this, and we will get the magnetization r convolved with the overall point spread function, and this has a real component, which is 0.5 times the delta function, plus some imaginary component. And then, if the magnetization is real valued, then the image is simply the real part of this convolution. The question, though, is how do we remove the phase when the magnetization is complex valued? Because now we will have a contribution from the imaginary part of the point spread function. So let's look at some examples. Here is the most common case of partial Fourier sampling when we have a contiguous partial k-space. So here we've sampled again just the negative k-space points. The odd component of the half-Fourier sampling function is a step function. And this means that the imaginary part of the point spread function is localized. Then if we assume similar phase across the region of the point spread function that has significant energy, and this phase is in the magnetization, then what we can do is we can apply a low resolution phase to demodulate this phase from the image, and this actually works quite well to reconstruct. And this is the basis of Homodyne reconstruction. So in Homodyne reconstruction, we'll do a partial Fourier acquisition like this, where we sample k-space, and we'll sample half of k-space plus a little bit extra. So we take the central part here where we have that little bit extra, and we have a symmetric k-space that is essentially low resolution or low extent in ky. We take the Fourier transform of the actual sampled data, and this gives us an image that is slightly blurred. We take the Fourier transform of the low resolution data, and this gives us a low resolution image. Now we can take the conjugate phase of the low resolution image and use it to demodulate the phase from the top image. And then we can take the real part, and you notice that the image actually gets sharper because we've suppressed the imaginary component of that point spread function by taking the real part. So this is the basis for the Homodyne reconstruction. It works generally fairly well. It doesn't work perfectly, and it has some assumptions, but at this point, the point spread function analysis should help you understand why this has some chance of working. So let's look at another question. What are the alternatives for half k-space sampling? Remember I said that you can choose either the sampling point at k or negative k. So this is another example. What if we sample the even lines on one side of 0 and the odd lines on the other side, which might look something like this? Well, in this case, the odd component is a step function modulated by e to the pi I times n, which is essentially alternating plus minus 1. What happens now is the real part of the point spread function is still a localized delta function, but the imaginary part is localized, but actually shifted by half a field of view away. In this case, it is actually very challenging to demodulate the phase, because if the phase varies between the central real part and the half field of view away imaginary part, then you won't successfully demodulate, suppress the imaginary component with a Homodyne reconstruction. So there are other options you can do here. You can do a partial k-space point spread function when you do a random selection. So if you randomly select samples at k or minus k, the half k-space sampling function might look something like this, and the corresponding point spread function now, because this odd part is basically a random plus minus 1, the imaginary part of the point spread function is spread out incoherently. So this may or may not help, and this is still a long debate in MR whether this actually helps to sample conjugate k-space points or not, and it depends a lot on what kind of reconstruction you're doing, as well as the characteristics of the object and the amount of background phase. So let's look now at k-space modulation. So many sequences acquire multiple lines where there are different signal levels at different k-space locations. So here are some examples. We have echo train sequences where T2 or T2 star decay over k-space can change the signal level. We can have magnetization prepared sequences where there are basically transients or changing signal while we're acquiring different lines. We can have EPI or spiral where we have off resonance, and off resonance is changing the phase as a function of k-space location. We can have temporal signal effects. These are often not due to, there are some of these that are not due to motion, such as contrast uptake, inflow signal enhancement, or varying background field effects. And in all of these cases, the point spread function is a function of the order in which k-space points are applied and the signal change over the time that these points are applied. And an example that is common is shown here, and you've seen this before, but it is proton density weighted spin echo train imaging. And here we might sample k-space something like this, where we sample the central k-space information first, but there is T2 decay over the echo train, and we might sample one direction outward and then the other direction outward. So we get this modulation here. And the result of this is that we have some point spread function amplification. So here the point spread function shows, you see the unmodulated point spread function, which is quite high. So we lose some signal when the signal decays. So the modulated point spread function is lower to begin with, but it also is slightly broadened compared to the original. Now we should also think about different ways to order our k-space and how these might impact the point spread function. So these are some common terms you might hear for the way k-space is ordered. So you can acquire k-space sequentially, so simply acquiring from the top of k-space to the bottom or vice versa. You can sample from the center out, as we saw in the previous example. You can do acquisitions where you interleave the acquisitions, so you're acquiring multiple contrasts repeatedly. So each color here represents a different contrast in k-space. And when we do interleaving, what we're trying to do is make the variation in k-space smooth. We can also do segmented acquisitions, where now we acquire a group of points that are close together in k-space. And this might actually work well because here, if there is some kind of a random motion in the background, this might actually lead to smoother changes in k-space. However, it is not that common. It's not nearly as common as interleaved imaging. And the reason being that if you have the signal modulations in the worst case that are shown by the colors on the right, the effect on the point spread function now will be a ghosting, which is generally worse than having a blurring type effect. So in all of these cases, you'll have some kind of modulation of k-space, and if you take the Fourier transform of that modulating function, you will convolve the point spread function with that, and this will give you the overall point spread function. So we'll end here with just an example of k-space sampling. Here we have a spin echo train. We're using compressed sensing, which we'll talk about in the next lecture. We have half-Fourier sampling, and we're not sampling the corners of k-space. So we've put together a number of different things that you've already seen at this point. So we're sampling in ky and kz. Notice that the center of k-space is actually on the right in this diagram here. So what we have is the different colors represent different echoes of a spin echo train. So we have a smooth modulation because we're basically keeping points on the same echo number close by. We have randomized sampling for compressed sensing, so we're randomly selecting samples in each region. And then we're choosing trajectories through these regions to actually minimize the change in the gradients so that we reduce eddy currents. So a number of factors here to try to keep the signal smooth across K-space so that the modulation effects have minimal impact on the image quality. Okay, so in this lecture about sampling and point spread functions, we've seen that the point spread function is the Fourier transform of the K-space sampling pattern. The K-space extent determines the point spread function main lobe width. The K-space density determines the point spread function replica spacing. K-space apodization determines the point spread function side lobe height. K-space modulation is a convolution of the point spread function with some function that depends on that modulation. We've seen that variable density and density compensation both affect the point spread function, and that half-Fourier sampling gives a real valued and imaginary valued component to the point spread function, and that the real valued component is a delta function, and the imaginary valued part should be considered carefully in reconstructing the signal. So the question then is, how might we extend this PSF approach and our understanding of it to different dimensions of sampling? And to do this, we should watch the next lecture.